So the topic of the presentation, as Amrit just said, is how a crystal forms from a solution, and in particular how NMR, solid state NMR, and hyperpolarization can help investigating this process. So here is the outline of the presentation. So I will start with an introduction of the subject, and in particular focusing on the experimental challenges of characterizing crystallizing solutions, and then I will step onto the experimental methods, and in particularly focusing on molecular organics. So I won't treat inorganic system. And after an overview of very quick of existing techniques, most of the presentation will focus, of course, of NMR. And in particular, I will show you how we are trying to find solution to solve these three challenges. So the presentation is structured in three parts, so you're welcome to ask questions whenever you want, but in particular, I think at the end of each part or at the end of the presentation, as you prefer. And quickly, I will conclude with future directions. So crystallization from solution is the process from which essentially we start with monomers, which monomeric entities can be molecules, but it can also be ions or atoms. This is the process that leads from isolated monomers in solution to a solid phase, which is ordered, in particular is crystalline. And in order to trigger crystallization from solution, usually we have to reach supersaturation, which can be done in several ways by playing with temperature, with anti-solvent, for example, and so on. But the problem is that today, we cannot really describe finally what's happening in this process to the entities, how they assemble to get the final crystalline form. And there is a real scientific need to try to understand the fundamental mechanisms of crystallization because of the need to try to control the outcome of crystallization. And this is particularly important when we deal with polymorphic materials, which are materials which have the same chemical composition, but they have different crystalline structures or solid structures. Because of their different structures, although they're chemically identical, they have different properties. And this is everywhere around us. So here you have a few examples, for example, in calcium carbonate, different forms, but you also have in materials, in food, in our bodies, in animals, rocks. And this process is also very important for chemistry. So it's almost everywhere. And the problem is that every time we change the structure, we change the properties of the material, so we affect their end use. It is a field in which polymorphism and crystallization control is particularly relevant, is pharmaceutical science, in which active pharmaceutical ingredients usually are composed of small organic molecules that are very prone to polymorphism. So that if you look at the potential energy surface of an average organic molecule in the solid state, we see that this surface is rather flat, and it contains several local minima, which corresponds to possible metastable polymorphs of the same molecule. And all these minima are separated by a few kilojoule per mole, most of them, of course, not all of them. So that inducing polymorph transformation is actually quite easy to do, and it happens many times, for example, during the manufacturing of the drug. And this can eventually affect the drug action, of course. So to try to rationalize all this polymorph transformation and possibly to identify the conditions that lead to the stabilization of a particular form that have specific properties for a specific use, many theories have been developed in the last centuries, I would say, because this first theory, which is the most long-standing one, it's the classical nucleation theory, has been standing for a long time, and essentially it assumes that from the monomer in solution to the crystal, we proceed by monomer addition of the monomers. So, and in all this first stage, there are two energy contributions that are counteracting one another. So one is the positive interfacial energy, and the other is the bulk energy, the negative contribution. And when the gathering of the entities reach a certain critical radius, the bulk energy overcome the interfacial energy, and this is the nucleus in this theory is the first stable entity that is considered to exist. And this entity has the peculiarity of already resembling the final crystal. And actually, this theory doesn't doesn't justify many of the experimental evidences that have been observed in the last 15 to 20 years, especially for inorganic compounds like calcium carbonate. And so more recently, there are many other techniques, many other theories that have been developed, which have in common the fact that they are multi-step. So they're just not the formation of the nucleus and then the crystal growth, but there is the possibility of the formation of intermediate forms, which can be even present in solution. And one of the most famous or studied theory is for sure the pre-nucleation cluster theory, which has been observed especially for calcium carbonate, in which it is established that there is the formation of pre-nucleation clusters in solution, which can happen even under saturated conditions. And these entities are dynamic entities that exchange with the solvent permanently, and then through a progressive solvent loss turns into some amorphous intermediate forms that then eventually transforms into the crystal. So you see that crystallization is more complex than one we expect on the basis of the simple classical nucleation theory. And so there are a lot of experimental challenges that comes with the investigation of this system. And I think that the first more important thing that we have to try to do is to be able to follow the sequence of events with sufficient time resolution. So sufficient time resolution can be really different depending on the system we are investigating. But what is crucial is to be able to identify all the forms through which the monomers transforms to the crystal. And the second important thing is that we don't only have to follow their transformation, but also to characterize their structure. And the characterization should, or at least requires, to go through different time scales. Requires to go at the atomic scale to understand what are the interaction among the entities in the different stages of crystallization, but also to reach nanoscale and even mesoscale, which is the average size of the crystal, the final crystals. And then another challenge, which is very important and specific to polymorphic solid, is to try to understand what happens when monomers, what makes a monomer to decide to go towards the formation of one particular crystalline form or another one. And if we think of the evolution of the concentration of the different species present in an ideal crystallizing solution in which all the species that I've mentioned in non-classical nucleation theories could be present, we could expect that at the beginning of crystallization, we have a lot of monomers in solution with some liquid phase present, for example, the pre-nucleation clusters. And then at some point, all the species entirely transforms into some other solid form, which can be amorphous or nanocrystalline or even aggregates. And then at some points, we have the formation of the first crystalline phase that then possibly transforms into some other polymorphs. But this is quite an idealized vision of what happens in a crystallizing solution, because in real crystallizing solution, what happens looks more like this, in the sense that we have overlapping of different species. The transformation of all the species is not simultaneous. So if we take a particular time point, we could expect to have a lot of different species simultaneously present in solution. And these species are chemically very similar, if not identical sometimes. What is changing among them is essentially their structure. So we are in presence of different particle size, lifetime, order, concentration, and physical state, because there are both liquid and solid species. So how do we deal with that? So there have been many techniques that have been applied to study crystallization, and specifically in situ, and there are a couple of reviews that I'm mentioning here that reviews all these methods, among which also NMR spectroscopy. And most of these methods are in situ, which means that the investigation of crystallization occurs inside the detection method, so the spectrometric or spectroscopic method that we are using. More recently, electron microscopy has really been showing a lot of interest because it allows to give images of crystallizing systems. And actually here I'm showing you just a couple of examples of what electron microscopy can give us in terms of the investigation of crystallization, non-classical crystallization for molecular organics. But these are very recent papers, and there are less than 10 of these papers around. So it's really something that is starting to grow. And you can see that we can see the formation of amorphous phases, their ordering towards, in this case of this dye molecule, towards some fibrillar phase. Or in the case of flufenamic acid and API, we can see the first formation of aggregates and the revolution towards crystalline phase more later. And we have an excellent time scale of about seconds, even milliseconds in some time. The problem of this approach is that, as you can see, we have beautiful images on the nanometer scale, but we don't have chemical information that comes from these images. And it's very difficult to reach information at the atomic scale. So this is where NMR comes into play. And you know, all know that it's very sensitive to the chemical environment of the atoms. And so it can be useful to try to solve the three challenges that I've just mentioned before. So in the rest of the presentation, I will focus on each of them and possible solutions that we have found until now using NMR. So the first approach that was developed was about 15 years ago. It was developed by Kenneth Harris, and essentially is an in situ NMR technique. And then for that, he decided to use a solid state NMR spectrometer, not a liquid state one. So one in which magic angle spinning is going on. And the idea was to use the temperature control of the spectrometer to trigger crystallization by a temperature jump. So essentially, we start with a solution which is supersaturated at room temperature. We warm it up inside the spectrometer, then we decrease the temperature, and then we try to acquire spectra at different time points. Which, if we use cross-polarization magic angle spinning, which is a good filter for solid phase, can reveal the formation of the first solid phase. And because the isotropic chemical shift of crystalline organic molecules is really a signature of the polymorph itself, we can even follow transformation into other polymorphs. And also detect the formation of the first particles, because when no solid is inside the solution, we shouldn't observe any signal in CP. And actually, this technique has been very useful because it allows just to monitor phase transformation as a function of time. So we can detect what is the lifetime of the different polymorphs and even discover new polymorphs. And in a more recent advanced approach, an in situ evolution of this in situ approach, they decided to also observe the liquid state spectrum by doing a sort of stroboscopical observation of a liquid and a solid spectrum. We have an almost simultaneous monitoring of liquid and solid phase, and this could possibly be helpful, for example, to detect pre-nucleation species. Although probably for reason of sensitivity, this wasn't possible. So what are the limitations of this in situ approach? Well, the first limitation is time resolution. And this comes from the fact that we are looking at a specific nucleus, which have specific relaxation properties, receptivity, concentration of the species in solution. And this essentially avoids the possibility of acquiring to the experiments, because while we are trying to acquire the signal to noise, a good signal to noise ratio, the crystallization is evolving. So 2D experiments are longer and it's difficult to acquire them. The second negative point is that we are allowing crystallization in situ in the presence of a strong magnetic field. And in some cases, it has been shown that magnetic fields can have an effect on crystallization. So it can modify the crystallization pathway. And then we have, of course, spinning at thousands of revolutions per second a solution inside a rotor, which creates gradients of pressure, radial gradients of pressure. For example, in a 4 millimeter rotors on the sleeves of the rotors spinning at 12 kilohertz, we can have a pressure of about 50 atmospheres, while it's 0 at the center. Okay? So it's really a big gradient, and in some cases can be really important in terms of crystallization. And then, of course, the last limitation is sensitivity, which is inherent to NMR. So the solution that we tried to develop to at least increase the time resolution of this approach was to try to investigate solutions which were not liquid while inside the NMR spectrometer, but to work on frozen solutions. So essentially, this time we have a solution which is undersaturated at room temperature and which becomes supersaturated at cryogenic temperatures. For that, we used an LT-MAS probe, the one that we have in a standard magic angle spinning DNP spectrometer. And then once the solution is frozen, we start to increase slightly the temperature as a function of time to see whether crystallization can occur under these conditions. Actually, in frozen solution, we can expect nothing happens, but depending on how frozen the solution is, we just actually reduce the molecular tumbling and the molecular diffusion, but some molecular tumbling, some molecular diffusion is still present inside. And so we tested this on glycine, which is a good sample to test crystallization, because all the polymorphic phases of glycine are well studied, well characterized, and the crystallization is well known. What we were expecting was the formation of the beta polymorph, which is a very unstable form of glycine, and its transformation to the alpha. So we use CP-MAS to follow this transformation. And here I'm showing just the carbonyl-carbon region. And you see that when we just freeze an undersaturated solution of glycine in water, we observed a very large signal which corresponds to the carbonyl-carbon signal of glycine, of glycine, solvated molecules of glycine. But as soon as I start increasing the temperature, this signal starts to disappear, and instead we observe the signature of a phase that looks crystalline. And this new phase is a new phase because its chemical shift doesn't coincide with any of the known forms of glycine. And if we continue to warm up the solution, what we observed is that this signal disappears in favor of another signal, which is this time we know, the corresponding to the formation of the beta form. So it was really crazy because it was the first time that the formation of the beta form in pure water was possible to detect using NMR, because usually beta evolves in pure water very quickly to the alpha polymer. And because of this extended time resolution that we can control partially by controlling the way we increase the temperature, we could even acquire these 2D experiments here, which are in which this headcore experiment revealed for this new polymorph the presence of a correlation with protons from water molecules, indicating that this polymorph was probably an hydrated form. And a few months before our study, a new hydrated polymorph of glycine was identified using powdered X-ray diffraction and CSP, crystal structure prediction. So probably this was the form. So to verify this, we acquired this 2D experiment, double quantum, zero quantum filtered experiment, which gave us a build-up curve, which only depends on the intermolecular carbonyl-carbonyl distances which are present in the crystalline phase. And this function can be plotted starting from a given structure. Okay, so we took the structure of the glycine dehydrate, reported from this paper, we plotted it, and it gave a very good agreement with our data. So it definitely was a dehydrate that we were observing in our study. So we have seen the limitations of in situ, in the liquid, in the study of liquid solution. What happens in frozen solution? Well, essentially we gain from the fact that we can increase the time resolution and so be able to acquire 2D experiments. And also that partially we remove the effect of magic angle spinning by freezing the solution, so the gradient of pressure is less important, but we still have the rest of the effect. Although by decreasing the temperature, we also partially improve the sensitivity. But overall, we still need sensitivity And we also need more flexible operational conditions because, I mean, studying crystallizing solution in the frozen state is not probably feasible for all the crystallizing solution that we want to explore. Here I'm stepping to the second part of the presentation, in which I try to show you examples of how we can partially solve this problem and get sensitivity. And this relies on the use of DNP. Okay, a magic angle spending DNP. This is a typical spectrometer. And usually what we need in DNP is cryogenic temperatures, and we need polarizing agents, okay, to transfer the electronic spin polarization to the nuclei under cryogenic conditions and in the presence of microwave irradiation. So the problem is that magic angle spin in DNP is, at least in its standard utilization, is usually have strict temperature requirements. So it requires to go at very low temperature for the polarization transfer to be efficient, and the saturation of the electronic spin states to be efficient as well. So so how it can be suitable for studying crystallizing solution that evolve with time. So the solution that we found was to use the DNP just as for NMR detection, but to allow crystallization to occur ex situ, so under standard room temperature conditions. And here is what we imagine. So we prepare a solution in which the radical, the species to crystallize are simultaneously present, to warm up the solution so that it becomes undersaturated, and then to transfer this solution to a certain number of rotors for MAS DNP, which are present outside the rotor at room temperature on the bench. And then the temperature drops triggers crystallization. And when the time has come for us to analyze the solution, then we insert the rotor inside the DNP at 100 K, and we collect the NMR snapshot. And by doing that at following times, by taking the other rotors in which crystallization occurs in parallel, we can have snapshot at increasing times. So we did that for glycine in the presence of amyopol, and this is the kind of snapshot we can have. In black, it's the microwave off, and in green, the microwave on spectrum. So essentially what gives us is that the information that, so the pathway that we were expecting to observe for glycine was simply the transformation of beta to alpha over a time frame of 24 hours, because the gamma is not feasible over these time scales. It comes later in months usually. So the signature, the spectral signature that we observe in the CP-MAS spectrum is indicates the presence at short crystallization times of the beta forms, which is dominating, some alpha and some solvated. And as far as the crystallization evolves, we observe the progressive disappearance of the beta form in favor of the alpha. And this pathway is exactly what we were expecting to see, which is very encouraging, because it means that the fact of flash freezing the solution doesn't impact crystallization. But the problem is that you can see that the epsilon here is very, very small. Okay, it's almost 1 most of the time. And this comes from the fact that it's very difficult to homogeneously distribute the radical in pure water. Pure water have a strong tendency to crystallize, and it's especially the time that it takes from the temperature of water to go from room temperature to 150 K, which is called the metastable cubic ice region, that we should cross as fast as we can to avoid the crystallization of water. But we don't control crystallization. We do the freezing. We just put it inside the spectrometer. So the solution that we found at the time was just to introduce a slight amount of a glass-forming agents like glycerol that improves the distribution of the radical in water. And here you can see that we could increase the sensitivity by a factor of 10 on some of the signals, at least. And this was also useful because it allows us to get this kind of 2D correlation in short times. And what is important is that this snapshot approach, because the system is not evolving at all when it's at 100K, gives us all the time we want to acquire 2D experiments. And here, for example, thanks to this carbon-carbon double quantum, single quantum correlation, we were able to detect the formation for the first time of pre-nucleation species clusters of glycine forming in solution. In fact, you can see that along the diagonal, we only see the intermolecular correlation between carbonyl-carbon region within the crystalline alpha structure or beta, but we also observe a very large signal here, which corresponds to the intermolecular interaction of glycine molecule in the amorphous phase. And if this is something that we can maybe think is possible in a supersaturated condition, even actually it shouldn't have been visible in our case, it's still visible even after 1 hour from the beginning of crystallization, when most of the glycine molecule are crystallized and the solution is no more supersaturated. So this is a clear indication that these clusters are stable even under undersaturated condition, which is compatible with the existence of pre-nucleation species. Okay, so this solution of adding glycerol was good because it increased the distribution of the radical into the solution, but we still have possible interference between the radical and the solvent. And this makes me do the transition to the third part, in which the solution that I am presenting now for selecting polymers also partially solve this interaction with the possible interaction with the radical. So what are practical ways that we can select polymorph? Essentially, there are two ways. The first way is to add additives to our solutions, which means adding a species, a molecular species that interacts somehow with some crystalline forms better or than with others, or some of the facets, for example, of a crystal, so that the formation of a particular polymorphs is inhibited and of other polymers is favored. So in this crystallization of glycine in pure water, we observed this this pathway, which leads, it's the other way down now. So it's the shortest time is at the bottom. So we have a dominance of beta and then beta to alpha transformation. But introducing introducing additives in small amount can induce variation in polymorph selection, in the kinetics. And what we observed, and interestingly, was also that it can improve the DNP enhancement. So we added different things. So one was glycerol that I've just shown you, which improved the signal to noise ratio, but not the kinetics very much and not the pathway. We also tested methanol, which was very good, modified slightly the kinetics. In particular, it was faster, the transformation to the gamma form over the same 24 hours, but not, but in particular increased the enhancement. And in particular, what we observe is using an ACL, we can change the pathway and stabilize the gamma form instead of the alpha. So the use of additives in DNP works, and it can also work in terms of enhancement, which is very interesting. So the other way that we have to modify and select the crystallization pathway is to use confinement, and in particular nano confinement. And this is something that has been observed before by different groups. There are two excellent reviews, if you are curious, by Michael Ward and Fiona Meldrum about these processes. And actually confinement really changes the crystallization conditions radically. Because essentially it modifies the polymer stability ranking. So this means that polymers that are not observed very easily in the bulk, which are even unstable in the bulk, can become stable and even stable for a long time. But how we can study this using DNP? So the solution that we found was to use this kind of radical agents, which were developed in our institute by the group of Stéphane Gastaldi and Eric Besson, which essentially are SBA15 silica materials that contains tempo face-to-face radicals inside the walls of the materials. And this had a lot of advantages for investigating crystallization because first, the interaction between the crystallizing species and the radical are eliminated because the crystalline species fill the pore but not enter the wall, or not supposed to enter the wall. And the radical is homogeneously distributed in the sample, so we don't need to add any glass forming agents. And so we can work in pure water in DNP without worrying about that. So this is what we did. We impregnated this material with a solution of glycine in water, which was undersaturated in our case. And then we allowed crystallization to evolve into the pores by evaporation. And then we applied the snapshot DNP approach that I've just shown you in the bulk, this time under confinement. So here is the first snapshot that we got on a solution of glycine in pure water after 15 minutes from the beginning of crystallization. And you can see that we have a very good enhancement, but this signal just corresponds to the solvated molecules of glycine. We don't see very much. So we had the idea that NMR is not just CP, okay? It's we can use a lot of different properties. And although we are in presence of a frozen solution and we can expect that the mobility of all the species is the same, this is actually not the case. And there still can be some gradient of relaxation properties that can be used in order to filter certain species from the other. And in particular, by using T1 row filtered, we were expecting to remove the amorphous phase and leave only crystalline phase in the spectrum. So of course, the relaxation means that the signal to noise ratio is lower and the acquisition is longer. But after 6 hours of acquisition instead of 2 minutes with a standard CP, we could observe something different. And what is interesting is that the evolution of this signal with a different snapshot after 1, 2, and 3 days of crystallization indicates that this probably amorphous phase turns into some crystalline phase after 2 days and disappears completely. So indicating that this is probably a precursor, amorphous precursor of crystallization. And this beta form, which is only visible thanks to this T1 row filtered experiment, wouldn't have been visible using standard CP-MAS. And what is very interesting is that these radical species are very powerful, not only because they allow DNP in pure water and so on, but also because they truly stabilize the metastable phases. And in our case, we could stabilize the beta form for more than 1 year in SBA silica materials at room temperature. But however, what we observed is that epsilon decreases with time. Okay, so I come to the end of my presentation where I want to just mention a few future directions that we can take to try to increase the efficiency of DNP in particular to investigate crystallizing solutions. And I think there are many things that we can do. The first is related to my last topic and to the sensitivity, increasing the sensitivity, because the pre-nucleation species that we are supposed to, we want to observe and we want to characterize are usually very diluted species. So we need sensitivity to increase the possibility of observing them, and also to we need the confinement in order to change the kinetics for having more chances to have the right time resolution to observe them. So the use of this polarizing matrices could be one solution for that. So these are hyperpolarizing polymers that have been developed by Théo Eldaray in the group of Sami Janin in Damien Montarnal, which essentially are similar to the silica in principle, but they have different pore sizes. And the difference is that while the pore size in silica is uniform, in these materials it's not uniform, it's distributed. And so we are currently investigating their use for crystallization investigation, but also for polymorph selection and screening. The other important point that have to be controlled more in the future is, of course, the freezing conditions of the solution. Right now, we are just freezing a rotor, okay, inside which contains a solution inside the NMR spectrometer. So this very nice simulation that was run by Arthur Pinon using COMSOL shows that in order to cross this metastable cubic height region by just inserting a 3.2 millimeter rotors inside a magic angle spinning DNP spectrometer takes up to 17 seconds. 17 seconds is too long, and surely we are forming microcrystalline water by freezing the solution in this way. So if you want to avoid that, a solution could be to freeze droplets, for example, on a cold copper plate, as Robert Tico is doing in his group for studying the dynamics of proteins. And you can see that now we can cross the region in about 1 millisecond. Or even we could freeze directly droplets of water in a cold liquid like isopentane, and this, depending on, of course, on the droplet size, we can have different freezing times. And the freezing time we are targeting is the order of 10 to the 5 degrees per second. So, and what is interesting is that if we reach this rate, we can hope to remove completely the need of a glass forming agents, which could be useful for many other applications. Partially related to this is the time resolution, because the freezing is low, we also have limited in time resolution, okay? Because if we reach milliseconds time freezing, then we can hope to reach milliseconds time resolution. But this is for the first point, okay, first snapshot we can get from the beginning of crystallization. But then the interval between two successive snapshots is also something that we have to work upon. And in this sense, I think that automation of sample preparation should be really the way to go, and will probably also help reproducibility of the analysis, which is very tough aspect to deal with. Of course, we have an NMR, and NMR is a panoply of infinite number of experiments that we can possibly run. And so protocols to separate very chemically very similar species are also important to implement. And the last point is computation. Because today, when we run molecular dynamics simulation, molecular dynamics simulation, unfortunately, is not working. It was a nice simulation video. This simulation here took in 2009 6 months to be run, and it was for trajectories of about 5 microseconds. But knowing that we need time scales of the order of milliseconds to seconds to observe in real nucleation cases. So we are still very far, and although in some cases we can reach the milliseconds time scale, and there are improvements that are being made all the time, but still there are a lot to do. And yes, okay, so it's running. See, it's very nice. And so this simulation are mainly used for estimating nucleation rates, by the way, and not for really investigating the mechanisms necessarily. Okay, and with that, I just conclude by thanking all the people that have been working with me on this crystallization project in the last 5 years, and in particular, Marie Jurami, who is now in Claire's Gray group as a postdoc, Paolo Ceraia Vioglio is now in Nottingham as a facility NMR DNP facility manager. Samuel Cousin, Romain Chèvre, Pierre Thureau, of course, was leading with me this project, all the rest of the group, Arthur for simulation, and Kenneth and Colin, who are with long collaboration on crystallization, people in Brooker, funding, and of course, all of you for your attention. Thank you very much.
Well, thank you so much for that excellent talk, Giulia. I think I can, on behalf of everyone, I'd really like to thank you again for accepting our invitation and coming here to share a little bit about your work today, and also for this excellent tutorial about how to do NMR in situ and observe these sort of crystalline systems, crystallization processes. And so with that, I think we are ready to take a few questions. So we have one question in the Q&A window. And so we have a question from Gabriele, who is asking, to increase your sensitivity by MAS DNP, is it a choice to go to higher field and faster MAS for better resolution, or would it be counterproductive because of even larger pressure gradients inside the rotors?
Well, so if we're still talking about DNP and we are working in frozen solutions, then going to faster spin and speed shouldn't be a problem. And actually, I think that would be interesting to go to pass the spin and speed for resolution, of course, for sensitivity in terms of indirect detection. For example, we could exploit a lot of new techniques that could give us proton also to get information about the solutions. Going to higher field, yes, in the sense that we still have a lot of quadrupolar nuclei that we could be interested in looking at. So going to higher spinning fields is necessary for some of them. For example, for oxygen-17 would be one of them. So yes, I think both. I mean, many developments, but surely these two would be interesting to explore for sure.
Yeah, that sounds very interesting. Since you, I mean, there are kind of two questions there that I also had. So, I mean, just thinking about DNP in general for these systems, can you comment on, from your experience, what sort of advantages does DNP provide in comparison to conventional variable temperature solid state NMR?
Well, there are many. I think the major advantage comes from the fact that, as I said, you can investigate crystallization under standard condition, which means that you can do whatever you need to crystallize a specific system, and then you use NMR just for detecting what's happening at a specific time point. And this you can only do it by freezing the solution. Okay, the principle of also cryo-EM approaches. But for that, it is really necessary that the freezing doesn't affect the crystallization itself. And this is something we have spent a lot of time working on to be sure that what we were looking was really corresponding to what's really happening inside, and that the freezing itself was not affecting the process. And for that, the fact of freezing faster is really necessary. I mean, it's one of the primary requirements and a future development that has to be done, because as the fastest you freeze, the more intact, okay, or more resemblant to a true snapshot your analysis will be. And this is something which is really important. So I think then for example, in the liquid NMR spectrometer, you are limited by what we can do with an NMR spectrometer. Okay, so you
no, I meant I think my question was more between standard, like conventional, like solid state NMR, but variable temperature solid state NMR. I guess what I'm asking.
Okay, sorry,
like,
I thought
DNP?
with respect to
right.
the yeah, well, the solid state NMR as the problem of the you cannot freeze it. Okay, you cannot so right. You cannot stop crystallization inside, so it's continuing to evolve. And then so this is the main limitation, the time resolution that you get, and of course the sensitivity, because DNP also should bring some sensitivity.
Yeah, I suppose if the enhancements were to improve more significantly, then maybe carbon-carbon inadequate experiments and so on could be more easily accessible in complex systems, I guess.
Yeah, but also sorry, just to conclude, what is also interesting is that if you freeze faster and you can remove the glass forming agents, so you can work in pure water, just the fact of freezing faster and making the solution amorphous should help increase the polarization transfer efficiency and should help sensitivity. So even with the same radical agents, not with new ones.
Yeah.
Sorry.
So we have another question from an anonymous attendee. Why is there a difference in enhancement for the amorphous form of glycine when it is confined versus when it is not confined?
Okay, so there is a difference in the enhancement when, sorry. Okay, just trying to go back to the slide, which is concerned by this. So if we look at here, I guess, this slide, you can see that the enhancement of the amorphous lysine is not the same as so here is not reported actually, but it's not the same as the alpha polymorph, for example. This is in bulk, okay? This is not confined crystallization. then probably, and this is due to the fact that we have a not homogeneous distribution of the radicals, so the amorphous glycine are in better contact with the radical because are sort of in the same phase, while the crystalline phases are sort of expelled from the solution, so the polarization transfer is lower. Although you can see that the beta and the beta and the alpha do not have the same enhancement, so it's also interesting, this fact. But probably then what you were mentioning is here, right? So you were mentioning why you mean why the enhancement decreases with time, or?
No, yeah, I think the question was like, why are those enhancements just different when they're confined versus when they're not confined? Yeah. So.
Okay. Yeah,
yeah,
because it's yeah. Sorry. So it's just because it's a different radical. Okay, it's a different way in which the radical is distributed with respect to the species we are polarizing. Okay, so I guess it's not the same conditions, and so we are not expecting to have exactly the same enhancement. And in one case is amipole, in this case it's just tempo, face-to-face tempo, but it's not fixed orientation. So I think the mechanism is not exactly reproducible and identical.
Sounds good. So I think the next question has to do with this addition of sodium chloride. So why does that increase the enhancement?
This is a good question. I think so. The hypothesis we are testing right now is that if the sodium chloride acts as somehow as a glass forming agent. I mean, it interacts with water. It breaks the hydrogen bonds interaction between water molecules and somehow prevents crystallization of water. This would be my interpretation. And this is why also, I mean, we add salt to ice to avoid, I mean, to lower the freezing temperature of, I mean, it goes in the same sense. And I think this is the reason why a better distribution, so a better enhancement. And
I have a follow-up question related to that. Have you looked at what the temperature of the sample is by using a different, like an internal thermometer? Because especially when you have a kind of a salt dissolved in water, I would guess that when you have, microwaves, maybe the microwave heating might be a little bit more than usual. I'm not sure if that's
this is
true.
possible. Actually, you're right. We haven't measured it for this solution. We have measured in water using KBR, but it's usually complicated to add some
for water
external, temperature control. We tried putting some KBR at the bottom of the rotor, then a plug, then a solution above it, but then spinning is crazy difficult. So it's not easy, but it's something that we should somehow try, I think.
The other effect that comes to mind is the effect that when you add particles, dielectric particles, and when they have a low loss tangent and a strong, real dielectric constant, the overall microwave power in the sample, the B1 microwave field is also much greater, leading to better saturation. There's this paper from the MC group back in, I think, 2015, 2016, something like that.
Yeah, sure.
And I see Gabriele is also pointed that out. But yeah, and I think my question is also very similar to what Gabriele suggested, that maybe they're not related because in this case, it's dissolved, and it's hard to say whether there would be an actual effect or not.
Yeah, exactly. It's very difficult to assess.
Yeah,
but you're right. I mean, every time you have solid particles and liquid particles inside, then you have some effect, dielectric effect that change, and it can impact the polarization efficiency, transfer efficiency.
Right. So we have another question from Ilya Moros, and he says, "Thank you for an interesting talk. Have you thought of exploring the state of silica surface, SBA15 silica? For instance, if the crystallization is performed in different solvents and the silica is activated in vacuum at different temperatures, that would have different water coverage and hence different acidity strengths. So I think he's wondering if that could affect the crystallization kinetics or the product."
Yeah, so you mean to pre-treat the silica in different ways and then allow crystallization to occur in these different silicas?
Yes, yeah, exactly. Yeah.
Okay, so no, we haven't tried, but the idea of modifying the surface is really one way to go, and especially because I mean if we want to work in pure water, then silica is easy. Okay, silica are easy because they have a lot of silanol groups, and water enters very easily the pores. But whenever we work, for example, with the organic polymers matrices, in this case we have to, if you noticed, I added 10% ethanol to the solvent, because it's not very easy to fill these organic polymers with water. So one of the ways to go would be to modify the surface, because as Giulia said, the interaction with the surface is sure the way that crystallization is triggered every time you have a surface is much more probable to have a heterogeneous nucleation than a homogeneous nucleation. So the surface really plays for sure plays a role. So yeah, it's very interesting to try. It would be very interesting. Yeah.
So we have a question from Shashanka. How much time does it take for getting a spectrum with the methods you described? If the crystallization completes within an hour, will it be possible to study the processes by the methods you discussed?
Well, if crystallization is complete within 1 hour, yes, because I would say yes, in the sense that the actual time resolution that we have at present is a few minutes. It depends how fast the operator is to prepare the rotor, close the rotor and run to the spectrometer, okay, to get the first point, I mean, of the snapshot. And it's actually what we do. So we run to the spectrometer and we insert it as fast as we can. So I would say the time resolution will be a few minutes. It's a few minutes right now. So yes, why not? I think it's possible. Then once it's frozen, then you have all the time you want inside the spectrometer, because for all the systems that we have investigated until now, within a few days, we didn't observe any evolution of a sample which is frozen in solution within the spectrometer at 100K. So I guess it's feasible.
So I have a question related to this. So how are you, so do you have your crystallization kind of going on in a separate vessel, and then you take the crystals or the precipitate, whatever comes out, do you take that at these different times, add it into your radical solution, and then freeze it? Is that what you do? Or maybe I'm misunderstanding this.
No. What we do is that we prepare super saturated solution at room temperature in the bulk. I mean,
right.
If you in the bulk and in confined is slightly different, in the sense that in the bulk we start with a super saturated solution at room temperature. We warm it up, okay, until complete dissolution of the species, because we want to start with monomers. Otherwise, you have grains and it's just crystal growth. It's not crystallization.
Yeah.
And then we transfer it into the rotor at room temperature, so the temperature drop triggers crystallization. But crystallization occurs inside the rotors already, and you have both the solvent and the crystals that form. And then when the time has come for you to analyze the snapshot you want, you just take the rotors and you freeze it. You can freeze it outside the spectrometer into liquid nitrogen, for example, and then transfer it into the spectrometer. It's tricky, but it's possible. Or just insert it into the spectrometer and freeze it in the side.
I see. So have you also considered trying maybe looking at systems? I mean, most of the systems that you talked about today, I guess all were from water, right? So from an organic solvent like TCE, which is naturally a good glass form. So have you tried something like that? Well, it's not a very good glass form, but it's reasonable.
Yeah, we have started to try using other solvents, especially because there are many organic molecules that do not like water. Okay, so
right,
crystallizing other solvents. So yes, we are starting. Yes, and TCE, yes, you're right, is a good glass forming agent. So probably all the problems that we have with water would be less important in organic solvents, hopefully, because it's really the worst solvent ever for TMP water. So
sounds great. So I think we have kind of reached the end of all the questions that we have. And maybe I can give it a minute more in case anybody else has any questions, and maybe ask another question in the meantime. I was also interested in in the build-up curves that you were showing at some point with the double quantum filtered build-up curves.
Yeah.
And so, I mean, just out of curiosity, when you kind of fit those build-up curves in that case, like how do you normalize for the relaxation or the recoupling?
Well, this is the interesting thing, that you take the ratio of double quantum and zero quantum filtered signals, which are actually evolve exactly the same sequence. It's not right, actually, because it's just the filter, which is the double quantum and zero quantum. So what you change is just the phase cycle during the acquisition to filter the coherence that it passed through a zero quantum or a double quantum. And by taking the ratio of these two, in the hypothesis, but it was verified that the double quantum and zero quantum relaxation contribution is the same, then you just remove the contribution of relaxation and you have a quantitative curve. Okay, that's
very nice.
You get rid of relaxation. And so this is not a fitting, it's just it's just a plot of a theoretical curve.